Group theory and its application to music. For the members, this includes June Vidial Alejado, Misty Glaze Cuevas, and Sincerely Yours, Shine J. Gonzaga. In math, a group is a particular collection of elements that might be a set of integers, the face of a Rubik's Cube, or anything. They follow specific rules or axioms. We have closure, associativity, identity, inverse, and commutative or abelian. Music involves creating patterns of sound, whereas mathematics is the study of patterns. And it is said that Pythagoras formed the connection between music and math when he heard a smith hammering the anvil. He found out that they formed harmonious beats because of the order of the weights which were being hit, which formed do, fa, sol, do of the music scale. This music scale consists of a discrete set of pitches having a repetition interval called an octave. Octave is an interval whose higher note has a sound wave frequency of vibration twice that its lower note. One way to effectively visualize the chords is to write all the 12 musical notes. Namely, we have C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and B. This will be further expanded as we go on along the video and determine if how the chords will be able to satisfy axiom. For the first axiom, let's start to take a look at this first example. If we take the P5, its interval is 7, going from 0 to 11. The P5 is 7, which is G. Now, if we take that and add another P5, we're going to add another 7. Now that will give us 14, normally with interval 14, and that corresponds to the major 9. So if we look on the piano here, the dominant is G, that's the interval 7. Now the dominant of the dominant, which is interval 14, gives us dominant, which is D. Now, since we're doing addition mod 12, and so once we get to the major 7, this is until here. That's it. Once we get to the major 7, we go back to 0 again. And so, 7 plus 7 actually gives us 2 addition mod 12. Well, that is interval 2, and that corresponds to D. So it's the same note as it would be outside the octave, but it's contained within the group. And that applies to any compound interval, and it has equivalent group element. Again, this one. So we see that because of that, the closure axiom is satisfied.
Now let's have the second axiom, which is the associativity. So let's have an example. So we have the quantity of major second plus perfect fourth plus minor 6 is equal to major second plus the quantity of perfect fourth plus minor 6. So in the left hand side, we got the minor second plus perfect fourth, and minor second from the table is 2 and the perfect fourth is 5. So we got the quantity of 2 plus 5, since 2 plus 5 is 7, and in the table we say that 7 is perfect fifth, which is dominated by G, and plus the minor 6, which is 8. So 7 plus 8, we get 15. Modulo 12, so we get 3, and 3 from the table is E flat. So applying it to the piano, we start from C, then to G, and then to E flat. So the same with the other side, in the right hand side, we got the major second plus the quantity of perfect fourth plus minor 6, and perfect fourth is 5, and the minor 6 is 8 from the table, and 5 plus 8 we get 13, and modulo 12 we got 1. So from that we get the D flat. 13 plus the minor second, which is 2, we get 15, and 15 modulo 12 we got 3, which resulted into E flat. Applying to the piano, we start with F, then goes to D flat and E flat. So we see that we end up with the same result from left hand side to the right hand side. Therefore, it satisfied our axiom. Third axiom, the identity. Here we are using addition operation, and our identity element is 0 by referring to the table, and our identity element, which is 0, is our perfect first. And relating it to music, adding perfect first to any interval, we're going to get the same interval as a result. Hence, the axiom is satisfied.
That's right, Miss T. Now we are going to move on to our fourth axiom, which is the inverse property, which is denoted by this. So, there has to be an inverse for each element such that when an operation is applied between the two, the result will be our identity or the element. So, this is where it gets interesting. For instance, our perfect fifth. So, the perfect fifth is our 7. Which is in the chord, it is the G. So, what are we going to add in the perfect fifth to go back to our identity element? So, it would be the fifth element or the F chord in the piano, or what we call the perfect chord. So, we're going to add the perfect fourth to our perfect fifth. So, 7 plus 5, we're going to get back to our identity elements, which is the C. So, as we all know that our perfect fifth and perfect fourth are inverted intervals. So, I'm going to show you how these two elements are inverted intervals. So, our perfect fourth, for example, has 5, 10, 3, 8, 1, 6, 11, 4, 9, 2, 7, 0, and our perfect fifth, we're going to have the inverse for this, which is the 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5, and 0. So that would be for the inverse property. Now let's move on to our final axiom, which is the commutative property. So it is denoted by this. So clearly, by reversing the elements, order is not gonna change the result. So if we're going to add the perfect fifth and perfect fourth, we're going to still gonna give us an octave. The major third and the minor third together still is a perfect fifth. So in fact, the difference between a major and a minor chord is the order of the minor and major third intervals within it. So that would be all.